Hello friends, welcome back to my YouTube channel. And in this video, I will continue my discussion on high pressure vessels. In my first video on the topic, I had introduced high pressure vessels to you. And in the second part of my discussion on high pressure vessels, I will be talking about axial or the longitudinal stress that is induced in the wall of high pressure vessels. So at the end of today's discussion, you will be able to derive an expression for this axial or longitudinal stress. Okay, so let us so to begin with, let us look at a typical thin-walled cylindrical shell and the stress that gets induced in the wall of the shell. It has components in three directions: axial direction, then radial direction, and tangential direction. The stress induced in axial direction is the axial stress or the longitudinal stress, which we are going to discuss in detail today. And then in the radial direction, you have radial stress, and in the tangential direction, you have the circumferential stress, or you can also call it as tangential stress. Okay, so if you look at each of the stresses, you'll come to know that one is perpendicular to the other two. So for example, axial stress is perpendicular to radial and circumferential stresses. Similarly, radial stress is perpendicular to axial and circumferential stresses. So each one is perpendicular to the other. Okay? And today we are going to discuss about the axial stress induced in the axial direction or the longitudinal direction. You call that axial stress or longitudinal stress. Okay, now let us consider the thick-walled cylindrical vessel. So we are going to consider vessel with closed ends. And now you can see that vessel, a cylindrical vessel where the ends are closed. And this is the wall of the vessel. Let DO be the outer diameter. So this would be the outer diameter of the cylindrical vessel. DI be the inner diameter. So this will be the inner diameter. And then PI, let PI be the internal pressure that is acting. And over here, we are considering pressure acting on the ends of the vessel. So one pressure acting on the top end and pressure acting on the bottom end. Then we will also consider PO, the external pressure. So one external pressure acting at the top, on the top end of the vessel, and external pressure acting on the bottom end of the vessel. Now the internal pressure PI, you can easily you can easily understand by looking at this diagram. The internal pressure PI is, or it tends to rupture the vessel axially. So if the pressure, since PI is acting in this direction on the top of the vessel and then on the bottom of the vessel, bottom end of the vessel. So the vessel, this pressure, it tends to break the vessel, rupture the vessel in axial direction. So PI may rupture the vessel into two halves in the axial direction. I hope this is clear to you. So the internal pressure PI, it tends to rupture the vessel axially. And due to this, it induces stress in the wall, and that stress is the axial or longitudinal stress. And this axial or longitudinal stress, we are denoting it by sigma A. What does it do? It opposes the rupture of the vessel. It counteracts the pressure force. To counteract the pressure force, stress is induced in the wall, and that stress, it is induced in the axial direction, and that's why we are calling it as axial stress or the longitudinal stress. Okay? And for our analysis, we will consider, let us know what are the forces involved in this process. So again, I am showing you the schematic diagram. We will consider upper half of the cylinder for our analysis. That is, this half of the cylinder we will be considering for our analysis. Now, what are the forces involved? First force is Fi. Now, what is this force? This force is due to the internal pressure Pi. And this force, it is resisted by the area Ai, which is nothing but the cross-sectional area based on the internal diameter of the vessel. That is, Ai is given as pi by 4 into di square. Therefore, force Fi will be given by this equation. Fi is equal to Pi into Ai. How you get this equation? Because pressure, as you know, Pi is the force acting per unit area. It is Fi upon Ai. Fi upon Ai. And from this, Fi will be Pi into Ai. And that is what I have written over here. So the force that is induced, or the force that is involved, one is Fi. It is due to the internal pressure Pi. It is resisted by the area Ai, and area Ai is given as pi by 4 into di square. And then Fi will be given by this equation. Fi is equal to Pi into Ai. And if you use equation for Ai, Fi will be Pi into pi by 4 into di square. And if you rearrange it, you can write it like Fi is equal to pi by 4 di square into Pi. Okay, so one force that is involved is Fi, which is due to the internal pressure Pi, and that is given by this equation. Fi is equal to pi by 4 di square into Pi. Then the second force is Fo, which is due to the external pressure Pu. And this force, it is resisted by area Ao, which is nothing but the cross-sectional area based on the outer diameter of the vessel. That is, Ao is pi by 4 into dO square. Therefore, Fo, that is force due to Po, it would be given by this equation. Fo is equal to Po into Ao. Again, same, we can say the same explanation applies over here, because Po will be Fo acting per unit Ao. Okay, so if you use equation for Ao, Fo will be Po into pi by 4 into dO square. That is, Fo is equal to pi by 4 dO square into Po. Okay, so second force involved is force due to the external pressure Pu. We are denoting it by Fo, and it is given by this equation. F0 is equal to pi by 4 dO square into Pu. Then the third force that is involved is the resistive force, which comes into picture due to the induced stress sigma A. Sigma A is induced in the wall of the vessel to resist the pressure force. Okay, so therefore the third force that is involved is Fa. And what is this? This is the resistive force that is due to the induced stress sigma A. And this force is resisted by the area E. And how it is given? How is this area given? EA is equal to pi by 4 dO square. minus pi by 4 di square. So we are talking about this area. So the resistive force due to sigma A, it is resisted by this area. And this area will be area based on cross-sectional area based on outer diameter minus cross-sectional area based on inner diameter. That is AA is equal to pi by 4 into dO square minus pi by 4 into di square. Okay, so if you have to understand it, I can just show you the top view for the vessel. You just try to understand. So this is the inner diameter and this is the outer diameter. And the resistive force that we are talking about will be resisted by this area. It will be resisted by this area. And this area will be given by pi by 4 du into dO square minus pi by 4 into di square. Inner area minus the outer area. That gives us this area, the area that is resisting the resistive force. Okay, so therefore, if you simplify, what you can do, you can take pi by 4 common. So therefore, AA will be equal to pi by 4 dO square minus di square. Now, Fa, the resistive force, will be given as Fa is equal to sigma A into AA. Because sigma A will be having units of Newton per meter square, for example, Newton per meter square. And then you are multiplying that with the area, which has units of meter square. So meter square and meter square will get cancelled out and you are left with Newton, which is nothing but the force. So in this case, the resistive force, it is given by this equation. Fa is equal to sigma A into A. And so in order to, how we got area AA, let me show you once again. So you have the outer diameter and the inner diameter, and we are talking about this area. We are talking about this area. And this area is then given by this equation. Okay, so Fa is sigma A into A, and if you use the equation for A, Fa will be sigma A into pi by 4 dO square minus di square. Okay, so in this way, we have understood all the forces involved. One is Fi given by pi by 4 di square pi, and this force is acting in the upward direction. It acts in the upward direction. Then the other force is Fo, which is given by pi by 4 dO square into Po. It acts in the downward direction. And then Fa, the resistive force, which is given as sigma A into pi by 4 dO square minus di square. It acts, since we are considering the upper half, so the force in the upper half will be acting in downward direction. Okay, so for upper half of the cylinder, three forces are involved. Fi acting in upward direction, Fo acting in downward direction, and Fa again acting in downward direction. Now we are going to take force balance. And what is that? Summation of forces in upward direction is equal to summation of forces in downward direction. Summation of forces in upward direction is equal to summation of forces in downward direction. Summation of forces acting in upward direction is equal to summation of forces acting in downward direction. So what are the forces acting in upward direction? There is only one, Fi. And how many forces are acting in the downward direction? They are two, F0 and Fa. So therefore you get this equation. Fi is equal to F0 plus Fa. Okay. And again, continuing with force balance. Force balance is summation of forces in acting in upward direction is equal to summation of forces in downward direction. And that is Fi is equal to Fo plus Fa as per our understanding. Fi is pi by 4 di square into pi, FO is given as pi by 4 dO square into PO. FA is given as sigma A into pi by 4 dO square minus di square. And if you use the equations, you have pi by 4 di square into pi is equal to pi by 4 dO square into PO plus pi by 4 dO square minus di square into sigma A. And pi by 4 can get cancelled out. So you have di square pi is equal to dO square PO plus dO square minus di square into sigma A. That is di square pi minus dO square PO. That is equal to dO square minus di square into sigma A. I have rearranged it. This term is brought on this side and you get this di square pi minus dO square PO, that is equal to dO square minus di square into sigma A. That is di square pi minus dO square PO divided by dO square minus di square is equal to sigma A. So this term is brought on this side. Therefore, sigma A is di square pi minus dO square PO divided by dO square minus di square, and that is the final equation for the axial stress or the longitudinal stress that will be induced. And this equation, we have for our analysis we had considered the upper half of the cylinder. So in the upper half of the cylinder, the axial or longitudinal stress that is induced, it is given by this equation. Sigma A is equal to di square into pi minus dO square into PO divided by dO square minus di square. So with this, I end my discussion. At the end of my discussion, I have told you how to get an equation for the axial stress that gets induced in the wall of a high pressure vessel. Okay, I hope you have understood the concepts. If you have any doubts, you please mention them in the comment section. For now, thank you for being with me. Thanks for watching my video. Do subscribe to my channel. Tell your friends to subscribe to it. And in my next video on this topic, I'll be talking about, I will tell you how to derive equations for radial and circumferential stresses that get induced in the wall of high pressure vessels. Thank you. Have a nice day. And I'm sure you'll be joining me in my next video.